All right, hey everyone, Mr. Hamilton here. Today we're going to be talking about work and power. Some of you have already seen these notes at least once before, or maybe copied them down or something. But there are some of you who have not seen these notes yet. Those of you that are in my class, you would be in that group. Today we're going to talk through kind of what are work and power in terms of defining them, and then also talk a little bit about how we calculate them and talk about the formulas. We're going to be doing a lot of these screencasts as we work through notes, as we do distance learning. So make sure that you're copying things down. Underlined things are still the most important things to have down, and make sure you write them down because you're going to need to submit a picture of your notes as part of the work for today's lesson. First, let's define work. So work is defined as a force applied through a distance. And then if you look at that letter A there, that's part of the key criteria for work being done, is that there has to be a force and then there has to be a distance, but there's also a third criteria of the fact that the force has to act in the same direction that the object moves that distance. So there's kind of three criteria for work. One is force, one is distance, and then the third one is the fact that the force and the distance have to be in the same direction. There's three examples listed here as well. So pushing or pulling a suitcase. So as long as you're pushing or pulling it and it's moving in the direction that you're pushing or pulling it, then work is done. If you're just simply holding a suitcase in your hand, meaning that you're not moving it up or down, you're just simply holding it, then technically no work is being done according to the scientific definition of work. And then that third example there, where if you are pulling at an angle, then in that case, some of the force that you're applying is doing work, but then some of it is not, because the angle is not, you're not pulling it directly at a parallel direction to the force and the distance. So when we calculate work, we're going to take a look at this triangle right over here. Many of you probably seen this already, but it's a good refresher for everybody. Calculating work is done by just simply taking the amount of force that's applied and multiplying that by the distance. So force is going to be measured in newtons, like we have in our previous units. Distance is always measured in meters. That's an important note. Sometimes you'll see distances in kilometers, so make sure that you always remember to convert it to meters if you're using the work equation. And then work is measured in a unit that we call joules, which is the same thing as what we call a Newton meter. So newtons times meters gives us what we call a joule. Okay, so that joule is a new unit that we introduced in this unit, but essentially it's equal to a Newton times a meter. Okay, force is required to lift object is its weight. So that last little note there in E, basically if something has a weight of 10 newtons, then we need to, at a minimum, apply a force of 10 newtons in order to lift that object. So if anytime you see weight, you should always remember that weight is going to be measured in newtons, because really what weight measures is the force of gravity that's acting on an object. All right, so we're going to work through a few sample problems here. I'm not going to show you like the whole guess method or any of that right now. Miss Viertz did another screencast video of some sample problems where she actually worked them out, and they're problems from your work and power problems worksheet that you have at home. If you don't have that worksheet, there's a copy of it in the folder for today's lesson as well. So I'll just kind of talk through these on here, but then I would highly encourage, and you'll probably have to, go watch the sample problems video that Miss Viertz recorded for you, where she kind of works through those problems on the whiteboard and shows you how to set them up using the guess method and all that stuff. So I'll kind of walk you through these ones here real quick, but it would definitely be to your advantage to go watch those sample problems as well that she's walking you through. So this one says a 22 Newton radio is lifted from the floor to the top of a 1.5 meter high file cabinet. How much work was done on the radio? So right away we see that it says a 22 Newton radio. That means that it weighs 22 newtons, or that the force that's needed to lift that object is going to be equal to 22 newtons. Okay, and then it says it's lifted to a height of 1.5 meters, which would be our distance. And so then how much work is done? Well, we're simply going to take this number, 22 newtons, times 1.5 meters, which is the distance, because we know that work is force times distance. So this is our force, this is our distance. So we're just going to simply multiply those two together. So we take 22 newtons times 1.5 meters. That would give us 33 Newton meters, which we know is the same thing as 33 joules. All right, another sample problem here real quick that we'll run through for work, and then we'll get into power. This one says a 320 Newton shopping cart, so again, that's going to be the weight of the shopping cart, just so you know, is pushed with a force of 50 newtons over a distance of 10 meters. How much work is done on the cart? So in this case, there's kind of what I call a decoy number in this problem, because you actually have two forces here. There's the 320 newtons and the 50 newtons. So in this case, the 320 newtons is actually kind of a decoy number here. We just don't actually need that number in this case because we're not lifting the shopping cart up. We're actually pushing the shopping cart. So the only force that we need to be concerned with on this one is the 50 newtons and then the distance of 10 meters. So this is going to be our force. This is going to be our distance. And we know that work is equal to force times distance. So we're going to take 50 newtons, multiply that by 10 meters. And it should look something like this. So 50 newtons times 10 meters gives us 500 joules. All right, so now going into power, we're going to kind of define what the term power is and talk about the equation here as well. So power simply means the rate of doing work, or the rate at which work is done. So essentially, the faster we do work, the more power we're going to exert. Okay, so to increase power, we're going to increase the work done in a given amount of time. So if we do more work in the same amount of time, we're going to increase power. Or if we reduce the amount of time and still get the same amount of work done, then we also increase power. So either increasing work in a given time or do the same amount of work in less time. Those are ways that we can increase power. For calculating power, we're going to use this triangle right over here, where it says that power is equal to work divided by time. And so work here is going to be measured in joules, like we just talked about. Time is measured in seconds. That's another important one to just keep in mind. And if you have a time that's in minutes or hours or whatever, in order for this equation to work properly, you're going to need to convert that into seconds. Power is measured in watts and can also be written as joules per second. So make sure not to confuse watts with work. Those are two different things. So make sure that you're always paying attention to what W we're talking about. There's another unit that we also use to measure power, which is something that many of you are probably familiar with. It's called horsepower. This is another unit used that was first used to compare the work done by a horse to the invention of new steam machines or steam engines. So basically, it's a unit that we just have a kind of a random conversion factor for, which is 1 horsepower is equal to 746 watts. So those of you who did the horsepower lab already, you should have found out that, your body can only generate about 1 horsepower or maybe a little less than 1 horsepower. In some cases, a little bit more than 1. But horses are pretty powerful. So one horsepower is quite a bit of power exertion. All right, so we'll go through a couple, or at least one example here, problem. And again, Ms. Viertz did a video as well, kind of walking you through the guess method of how to do some of these. Power problems, in some cases, can be multiple steps, because often you're going to be asked to solve for work first and then solve for power. So in that case, make sure you do the work calculation first and then the power calculation. This one here happens to be a simple one where the work is already done for you. So in this case, it says a person does 50 joules of work in 10 seconds. So 50 joules divided by the time of 10 seconds is going to give you the power here. So power is equal to work over time. 50 joules divided by 10 seconds would give you 5 joules per second, which we know is the same thing as a watt. So 5 watts would be the amount of power exerted in that example. Here's another example. This is going to be one that is kind of a two-step process here because it gives you a force, it gives you a distance, and it gives you a time. So in this case, it says a mover lifts a 200 Newton box, so that's your force, onto a 1.5 meter high truck. So he's lifting it up onto the truck, and it takes him 3 seconds to do that. So in this case, you can't just simply solve for power using the numbers that you're given. You actually have to solve for work first, and then once you get the work number, then you can solve for power. So work is equal to force times distance, as we know, as we covered earlier in the screencast. 200 newtons is the force, 1.5 meters is the distance, and so therefore he did 300 joules of work. So now that we know how much work he did, and we know how much time it took him to do that work, then now we can figure out how much power was needed in order to do that. So the power we know is equal to work divided by time. The amount of work is equal to 300 joules, like we just found. We divide that by 3 seconds, which is the amount of time it took him to do the work, and then that comes out to 100 joules per second, or we can just do it simply as 100 watts. So a joule per second is the same thing as a watt. Another example really quickly here. It says a woman uses 48 watts of power to push a shopping cart a distance of 30 meters in 25 seconds. How much force was used? So in this case, we're not solving for power, but rather we're going to solve for force using power and distance and time. So in this problem, we're given a power number of 48 watts, we're given a distance of 30 meters, and we're given a time of 25 seconds. So what we need to do first is figure out how much work was done. And so we can actually use the power equation, in this case, to solve for work. So we're going to rearrange that triangle, or we're going to use the power triangle here, and we're going to say that work is equal to power multiplied by time. So in this case, we're going to take 48 watts, which was the power, multiply that by the time of 25 seconds, which comes out to 1200 joules. So now we know how much work was done. And in this case, now we can do kind of the second step of this problem, which is to use the work equation and solve for force. So we're solving for F instead of solving for W. So force is equal to work divided by distance, if you look at your triangle. And so in that case, we'll take 1200 joules, divide that by 30 meters, and that would equal 40 newtons. So 40 newtons is your final answer to this problem, because what it asked us to solve for was how much force was actually used. So 40 newtons of force is what was used to push the shopping cart. We're going to stop there for today. If you have questions or need clarification on things, we will be having office hours throughout the day and the week. So please feel free to stop in on Google Meet and visit with either myself or Ms. Viertz or Mrs. Erdahl if you need to get questions answered. And again, if you want to do more sample problems, or if you want to see the actual guess method, Ms. Viertz is doing a video on that as well. And so you can check out that video for more help with doing the problems. So